Let us start today with the geometrical analysis for the solution of an LTP. So here, so suppose this is the data which is given to us x and corresponding y points. What is our main work here? We will consider here Chebyshev criteria to fit the model y equals to cx in the following data set. That means as we have done also the interpolation problem, what we do here, that the original function form is not known to us. What we have to do, given a data set, we have to just approximate, or we have to just bring or fit a curve which will fit the data accurately. Okay, so that is the main aim which we want to follow here, and for this purpose we are following out of various criteria. We are following the Chebyshev criteria to fit the model. This is our y equal to say, that is the approximate data curve to the following data set. Okay, and the optimization problem that determines the parameter c. See here, y equal to cx. C is the unknown parameter. So what curve we will take? We have just decided to take linear curve. Y equal to cx is just a line. Okay, but what will be the exact form of the linear curve wholly depends on this c. Okay, so we can say, suppose I am giving example y equal to x, I can take y equal to 2x, y equals to half x, and anything is possible. So which one will be best in our purpose to suit or to fit this data? Okay, for that we have to measure first the error, and then corresponding to a choice of the error function, we have to measure the or fit or bring the curve which will give the minimum error. And there are many criteria or many ways in which we can measure this error. Okay, and here as we are saying, we are using the Chebyshev criteria. So what actually they are doing here, let me just give the formal part first. They are considering the Ri as a new variable, which is nothing but the modulus of yi minus y of xi, that is the residual or the error. Okay, and then they are taking the minimum of this, all this, sorry, they are first taking the largest absolute value of this Ri, naming it as R, and then minimizing this R subject to this constraints. Okay, now let us just get the idea how they are going to get this whole thing as a just a minimization problem. Okay, so first and foremost of all, here is the thing, this say is the data set which is given to us, and we are trying to fit the curve y equal to cx in here. Okay, and as I am saying previously also, this is not the only data curve which you can find. You can use anything. So suppose you could have used a parabola, you could have used a cubic function also. Okay, or a sine function, cosine function, anything. Okay, first and foremost of all, we are restricting ourselves to polynomial functions, and as I said, we are trying to analyze here the geometrically the solutions of a linear programming problem. That's why we are not going into higher order, that means we are not going to degree greater than 1. So we are sticking to the linear degree, that is x. Okay, so if you stick to the linear degree, then this is the obvious, or this is the only polynomial which is possible to use as an approximate data curve. Okay, so we are taking this as an fx, y equal to cx, and let us just assume ki c is greater than 0. As c we are going to just find out, we are just considering c greater than 0. So suppose this is in general, I am saying, this is not I am taking y equal to cx. Suppose I have just used this as my data curve. Suppose I'm not going to, I'm just not saying this one, because this is a linear one, this figure will not come in that case. So suppose I have considered this one as my data curve, and suppose these are the points x1 y1 x2 y2. This, suppose this point here is x1 y1. Okay, let me just enlarge it a bit. This point is x1 y1, and corresponding point on the data curve which we are assuming here is x1 comma y of x1. Okay, again, so if this is the point on the data curve, that means by the curve which we are approximating, if you follow that curve, then this is the value of the ordinate, this whole thing. But actual value of the ordinate is this much. So what is the deviation? This much, this dotted portion is the deviation. So y of x1 minus y1 in this case, because y of x1 as we are drawing in this figure, it is greater than y1. So definitely this is greater than 0. Y of x1 greater than y1. Okay, again, suppose you take this point as this, here I have taken q1 as that point, here you take q2 as the next point, x2 y2, and corresponding to the data curve, let the point be this one, x2 comma y of x2, because whatever data you have taken, say suppose y equal to gx, you have assumed this functional curve y equal to gx, then according to this x2 comma y of x2. Okay, so here the deviation is this much, and here y2 is greater than y of x2, so y2 minus yx2. Similarly, we can continue to take on all the corresponding data points on the data curve and the points which are given in the data table, and just find the deviation in each and every of those cases. Okay, and as we can see, sometimes this y of x1 or y of xi is greater than yi, and sometimes this yi is greater than y of xi. So it is better to just consider here the magnitude. We are not considering here the signature. Okay, we are just considering the magnitude, that is the distance. Okay, so depending on that, we are defining, or rather just considering a new variable ri. This I am saying deviation in the main lecture material, they are saying it to be the residual error. Here they are saying it to be the residual error, largest possible. This is the residual or the error. Okay, acha. So this thing is created or just generating like this. For every point you are going to get this residual or error. Okay, or that is the deviation. Now, according to the criteria which we are following, the Chebyshev criteria, what we are trying to see, key curve for the deviation to measure, what we are doing, we are just finding out the maximum of all these errors. See, for each and every point there's an error. Obviously, as we are seeing here, for each and every point there is a difference. In some cases, maybe that is not the case always, but maybe this is equal to 0, but not in all cases. Okay, so we are just measuring the deviations in each and every of the point case, and then we are taking the maximum of all those deviations. Okay, maximum over I. This is a strategy we are considering here, and I'm just considering this is a new variable, small r. Okay, then you see, we are posing it as an optimization problem. How? Just depending on the motive which we are considering here. What is our main motive? Our main motive is to fit a curve as accurately as possible. Fit an approximate curve as accurately as possible. So this is our main motive here. Okay, so as accurately as possible, when will that be possible? When this deviation will decrease, not on for one point, but for each and every point this just deviation will decrease, then that curve is a more better curve for our purpose. So for that thing, we are using the strategy key. Okay, you are considering the residuals or the errors, you just consider all the errors, then you find the maximum of all those. So suppose there are 4 errors coming, 0.2, 0.3, 0.4, 0.5. So 0.5 is the maximum. Okay, so if 0.5 is the maximum, what I am doing, I am now considering, here I said I gave a numeric value, 0.5. So suppose considering one curve, suppose I have considered one curve, say y equal to g1x. For that, this maximum error is coming to be 0.5. Again, I consider another curve where the maximum error is coming 0.45. Again, I consider another curve where the maximum error is coming just 0.3. So which one is the better of all these three? The last one, because it is giving the maximum error as the minimum. 0.5 is the maximum error in first case, 0.445 is the maximum error in the second case, and 0.3 is the maximum error in the third case. So the third case is the most suitable case because this is giving the maximum errors minimum value. So maximum errors minimum value, this is the strategy we are doing. So maximum error we are calculating using the card which we are assuming and the data points. Okay, so the card we are assuming contains some unknown constant. So this maximum when we are deriving will depend on the unknown constant. So now depending on the unknown constant, if we just minimize this maximum error, that means if we minimize this r variable, then our purpose is done. Okay, so that is we are doing minimization of r we have to perform. So this is the optimization problem which we are considering here as a linear programming problem, and we are just going to just analyze the geometrical idea of its solution. Okay, so as you can see from here, say suppose r here we are using, and I am just giving the example r4 is the minimum. Okay, so r equal to r4, so what about the rest? R will be, yes, so suppose I am giving r equal to r4, so instead of greater than, you just put r equal to r4, but r4 greater than every other ri, where I is equals to 1, 2, 3, 5, and anything other than 4. Okay, so this one which you are getting, and this r0, or this is not the r0, this is r only. Okay, so this r is depending on the c. If you consider y equal to cx, I'm not referring to this figure. If I consider this equation 1 now, y equal to cx, that is a problem which we are just dealing here as the data curve. So this c is the unknown, as I said. So what this minimum value, that is, sorry, the maximum, R, and minimization of R will depend on this C. So R depends on C, okay, from the equation 1. So what? Now we are getting a suitable, or rather a well-posed linear programming problem. You minimize R. Minimize R means you minimize a function of C subject to some constraints. Okay, subject to some constraints, you minimize the function of C. So that is the thing which we are going to do here. Okay. So now, acha, now how the constants are coming? Here they are giving a list of constants, right? How the constants are coming. So up to this we are just clear key, okay, what we are actually trying to minimize here. We are trying to minimize that is the largest absolute deviation. That is the maximum of all the Ri you are just trying to minimize. Okay? Because once this is minimized, then that will give you the best suiting or best fitting curve. Okay. Now this, for this constraints, you just see key what is Ri. Ri is the absolute value of yi minus y of xi. Y absolute, as we have already said, we do not know which one will be greater or less. Okay, so whatever small r is the maximum of all these Ri. So I can just simply say ki r is maximum of this modulus or this absolute value. So for all I, this is less than equal to r. Yi minus y of xi is less than equal to r. So if you just break it, what you will get? Minus r less than equal to yi minus y of xi less than equal to r. Once you take this portion and another time you take this portion, for this one you will get one constant, and again for this one you will get one constant for any I. So for each I you are getting two constants. So suppose there are 3 data points, you will be getting 6 constants in total. For example, I am taking this one as a specific example. This one, what is the first point? For I equal to 1, x equal to 1, y equal to 2. So y1 is 2 and y of x1 is what? C, because cx, y equal to cx you are considering as your curve. So y of x1 is equal to c of x, c into x1, and x1 is 1. So y1, y of x1 equal to just c only. Again y of x2 will be 2c. Again y of x3 will be 3c, and y1 will be 2, y2 will be 5, and y3 will be 8. Okay, so I'm just considering the first one. Okay, so for I equal to 1, you are getting what? 2 minus c as the deviation, because yi is 2 and y of x1 is 1. So y of x1 is, sorry, y of x1 is c. Okay, so 2 minus c is the deviation. Okay, so 2 minus c will be satisfying this relation, minus r less than equal to 2 minus c less than equal to r. Now once you consider this portion minus r less than equal to 2 minus c, what you will get? Just bring it, minus r you just bring out on being in this side, so you get r plus 2 minus c greater than equal to 0. So this is the second constant you can see here, and again you consider 2 minus c less than equal to r. For this one which you are getting, r minus 2 minus c greater than equal to 0 from this part, and this is giving you the first constant. So once you take the first data point correspondence, you are going to get the first two equations. Similarly, for the second two will be given just by considering the second data point. That means what you are getting here, suppose y of x2 is 2x, sorry, 2c, not 2x, 2c, and y2 is 5. So 5 minus 2c. Okay, so 5 minus 2c, once it will be here, just put 5 minus 2c. So r plus 5 minus 2c and r minus 5 minus 2c. See, here you are getting this. So the pattern remains the same, only just according to the point, whichever point you are choosing, this will change. Again it is 8 and 3c. So 8 minus 3c. So once it will be r plus 8 minus 3c greater than equal to 0, and once it will be r minus 8 minus 3c greater than equal to 0. So ultimately we are now facing the problem of finding the minimum value of the r subject to these constraints. Okay, and as we can see, this r is obviously, yes, there is nothing non-linear involved in it, everything is linear. So it is a linear programming problem or linear optimization problem which we are dealing now. Okay, so now, so if you want to geometrically just have the idea of what we are doing for linear programming problem here, actually, as here only we can get the idea ki we have an objective function which is to be minimized or maximized. Okay, and there are some constraints. Okay, And as we have already discussed before, here it is a linear programming, so everything involved is linear. The constant is linear, the objective function is linear. Okay, so considering the constraints, what we are actually getting here, a linear programming problem has the property the point satisfying the constants form a convex set. That means if I consider say 2 points satisfying the constants, then obviously any linear combination, or that is any line joining these 2 points, will always satisfy the constants. Okay, so actually the constants in this case satisfy convex set criteria. Okay, so that means suppose you have in your hand 2 points, say P1, P2. Okay, such that P1, P2 both are satisfying the constant, say Ax plus By less than equal to C. So this is your constant. P1 is satisfying, say P1 is the point X1, Y1. So this is the thing we are getting from here. Due to P1 satisfying Ax plus By less than equal to C. Again, P2 satisfying will give you Ax2 plus By2 less than equal to C. Okay, now we are taking a linear combination. Lambda portion of P1 and 1 minus lambda portion of P2. That means actually geometrically what we mean, we are taking just nothing but a ratio, that is a division of this P1, P2. That is any point joining P1, P2 I am taking. That is a straight line P1, P2. On this I am considering any point, and this point will be given by lambda P1 plus 1 minus lambda P2. Obviously we have this idea from the vector, right from the vectors part. Okay, and you vary lambda, you get one after another point on this straight line. So any point you are considering from the straight line P1, P2. Okay, so if this P1, P2 is satisfying the constant, so simply you can see now I am checking whether any point from this straight line will also satisfy the constant or not. Okay, so I am just using the point lambda P1 plus 1 minus lambda P2. So lambda P1 plus 1 minus lambda P2 will break like this. This is the axis part, this is the ordinate part. Okay, so just on simplification you are going to get ultimately as P1 is satisfying this criteria, and again P2 is satisfying this criteria, so as a whole you are getting key A of lambda x1 plus 1 minus lambda x2 plus B of lambda y1 plus 1 minus lambda y2 is less than equal to C. So that means the point Q, which is nothing but the linear combination of P1 and P2, is also satisfying the same constant. So that is what they are saying in case of linear programming problem. Okay, had it been non-linear, we could not have said like this so much easily. So for a linear programming problem, this is obvious if any point is satisfying the constants provided, then you take the combination of all those points, convex combination of all those points. That is the requirement. Okay, not only you take any combination and it will give, we cannot say like that. You have to take the convex combination, that is lambda and 1 minus lambda. This adds up to 1. That means you have to consider any line, any point lying on the line joining the 2 points you are considering. In that case, that point also will satisfy the constant which is given. Okay, so ultimately that is the thing they are saying here. The point satisfying the constants form a convex set. Okay, and here the non-negativity is sometimes assumed the variables which you are using are positive. Okay, and depending on whatever constants are given, the whole 2D plane, here if you are considering two variables only, then there is a 2D plane. So the 2D planes get just divided into two parts depending on the constant. On a single constant it gets divided into two parts. Okay,